Hi, my name is Maanasa Muthukrishnan, and I'm a senior at Paul Laurence Dunbar High School, and I'm in the Math, Science, and Technology Center. I've recently completed my capstone research project on how game theory can be utilized to show cooperation. I've worked under the mentorship of Dr. Jeremy Van Cleve at the University of Kentucky's Department of Biology. First, I'll begin with an overview of my presentation. I'll start with the background of my project, then I'll move on to my question and hypothesis. I'll explain my methodology and the results that came out of it, and I'll go on to my discussion and future research. Last, I will mention my acknowledgements, and then I will give out my email for any questions. The purpose of this project is to create a base code that can be used in specific populations and help create a realistic way to show how danger works in animal populations through game theory. The reason that species cooperation needs to be modeled is because it creates a good idea of how animals are going to interact with each other in times of danger in order to compare to fieldwork. Animals interact in a similar way that humans do, including things like social interaction and cooperation. Games, such as the prisoner's dilemma, can show moments when cooperation between animals is needed, and the decisions that make the best outcomes through the Nash equilibrium. The Nash equilibrium gives the best possible outcome that gives benefits to both players. This project focuses on simulating game theory in order to show species cooperation. By using Julia, which is an imperative, functional, and object-oriented programming, it's possible to take a game like the prisoner's dilemma and turn it into a simulation to help as a model. This helps show the cooperation that can happen between species. In Binmore's Introduction to Game Theory, he describes the outcomes of the prisoner's dilemma based on the decisions of two people. If one person confesses, the person who failed to confess is convicted and sentenced the maximum term in jail. If both confess, then both will be convicted, but the maximum sentence is not imposed. If neither confess, both are framed for a different conviction with a different sentence. The Nash equilibrium for this scenario would be both players cooperating in order for the best outcome. In the image on the left, it shows that if both players defect, then they both get 9 years in prison. If one cooperates and the other defects, the one that cooperated gets 10 years in prison. If both of them cooperate, then they both get 1 year in prison, making the most equal and best outcome for both players being cooperation. My question is, how can game theory be used to simulate the way animals cooperate in times of danger? I hypothesize that if game theory is used to model animal cooperation, then the Nash equilibrium will be shown and it can be applied to animal populations. The base for my code is taken from Acknowledgements' code over social inheritance and the structure of animal social networks. The code uses dynamic generative models based on simple processes to predict network scale patterns that those processes are expected to produce, and then they compare them with observed networks. The model gives implications for how the inheritance of positions in social networks is interpreted. It allows for the estimation of social inheritance by using the random bonding parameters of Pn and Pr. The image on the left shows these bonding probabilities. The red dot is a newborn in a population. It's connected to a yellow dot, which is their parent. It's connected by Pb, which is a dotted black line. Pb is the probability of this newborn bonding to their parent. The parent is connected by two solid black lines to two blue individuals. These are the parent's friends. The newborn is connected to these friends by blue dotted line, which is Pn, which is the probability of the newborn bonding to its parent's friends. The newborn is also connected to two more blue individuals by a red dotted line. This is the probability of the newborn bonding to random individuals in the population. Next, I converted Binmore's prisoner's dilemma from JavaScript to Julia. The two codes were integrated by taking the probability values of Akshay and Alani, and then the outcomes from the prisoner's dilemma were taken from those chances. The experiment was broken into two parts. The first part had Pn and Pr increasing together and had the same probabilities. The second part had Pn and Pr changing inversely to one another. So when Pn had a low probability, Pr had a high one. The probabilities increased or decreased by 0.05, and it was run through the code. It was run for 200 trials, and then the trials were averaged and graphed. The probability of the organism bonding to their parents was kept the same the entire time at 0.9. The assumption that the organism would bond to its parents was made. Even though this isn't the case for many species, it is kept as a constant throughout the trials. This table shows the general definitions of bonding probabilities and then the experiment-specific definitions for the bonding probabilities of each part. The first part of the experiment showed that as the probabilities of Pn, which is the probability of bonding to the parents, the friends, and Pr, which is the probability of bonding to a random individual in the population, increased, then the likelihood of cooperation increased as well. The graph shows the probability of bonding versus cooperation. The x-axis shows Pn and Pr as they are both increasing. The y-axis is the average number of cooperation in the trials. The graph has a positive correlation that is very close to 1. For part 2, where the probability of Pn was growing and Pr was decreasing, the results showed that the average number of cooperation stayed relatively the same. As the probability of bonding to their parents' friends increased and the probability of bonding to a random individual decreased, the likelihood of cooperation in the population stayed in the same range throughout the trials. The x-axis of this graph shows Pn as it increases. It's assumed that as Pn is increasing, Pr is decreasing at 1 minus Pn. The x-axis is the average number of cooperation for the trials. The graph shows a strong correlation between the two variables as well. The results from the first part show that an increased probability of the species befriending one another will give better benefits to the population. This helps ensure that high bonding probabilities means that the organisms are more likely to work together in face of danger. The second part showed that as long as the species cooperates one way or another, then the majority of the population will choose to give back to the entire population rather than themselves. For the first part, the Nash equilibrium was favored towards the end of the trials. This was because the bonding probabilities were higher, meaning that they would cooperate with one another because they had better relationships with one another. The Nash equilibrium was favored for the majority of the time in the second experiment because as long as the organism found one way to work with the members in its species, whether it was its friends that the parents made prior or the random individuals in the species, then they would still work together and would rather work as a group than for themselves. The code can also be useful in showing the cooperation between animals based on these probabilities of creating relationships with one another. This has the ability to be used as an indicative model for how animals can work together. For example, you can take these results and compare them to fieldwork as a perfect world. You can also verify fieldwork with expected outcomes. So if you're going into a field and you're expecting one thing from this code, you can compare how they work together and compare how they didn't. For further research, I would like to include the population size in the code in order to account for how many individuals need to cooperate with one another in order for the species to survive. This code doesn't take in how many individuals are in the population. Cooperation differs between how many there are, whether it's 5 or 1,000. Next, I would like to make it more user-friendly, meaning I would like to make it easy for specific probabilities to be plugged into the program in order to simulate the probability of cooperation for specific species. I like to expand the parameters for multiple players rather than basing the interactions between two organisms only. In many cases, more than two organisms will have to work together in order to get the job done. Last, I would like to verify the code by comparing it to collected data from fieldwork in order to make sure it gives outcomes that are realistic. I would like to thank my mentor, Dr. Jeremy Van Cleve at the University of Kentucky's Department of Biology for his guidance in my project. I would like to thank the Kentucky Young Researchers Program for providing funding for research. I would like to thank Mrs. Karen Young in the Math, Science, and Technology Center for giving me this opportunity to conduct research as a high school student. Last, I would like to thank my friends and family for giving me support along the way. If you have any questions, you can email me at maanasa.muthukrishnan@gmail.com, and I would be happy to answer them. Thank you for listening.